on this
Oh.
computer. Good afternoon, Miss Manley. Thank you for sending in your application.
Good afternoon.
We've reviewed our. I'll be your interviewer for today. We've reviewed your application, and in the meantime, I'll be giving you a problem for you to answer.
Okay.
So, if you're looking at the Google Doc right now, I will give you the answer. Your task for today is to write a program that will check if a binary tree is symmetric or not.
Okay. Also, I think you should screen share so it comes up on the recording.
You are probably right, Miss Manley. Good catch.
Okay. So, the question is if a binary tree is symmetric or not.
Perfect.
So I'm assuming for the algorithm, I will be working on a method, and it will most likely take in the root of a binary tree.
Yes, you
and
could
from there,
do
I
that.
should determine based on the binary tree if it is symmetric.
Exactly.
So I'm just going to speak out the algorithm I expect I'll probably be using, and then I will write out the code.
Feel free to open up a window with MS Paint or Photoshop, put your ideas on paper.
Okay. I have a paper next to me, so if I'll write down anything I think. So, I have a question. So when you say symmetric, is this in the implication that it is you could say a perfect binary tree, such that every single node is filled and the heights are the same on both sides, and every single node has just 2 children except for the leaves?
The definition of a symmetric binary tree is that the node layout on one side is a perfect mirror on the other side. I'll give you an example here. If you look at this image I will put on the Google Doc, these are examples of symmetric binary trees.
Okay, perfect. So it does not necessarily have to be a perfect binary tree, it just needs to be symmetrical. Okay.
Yes.
All right then. So I see an algorithm that I could use where I end up checking one side of the tree first.
Mm-hmm.
Or instead, actually, no, I would probably end up creating a method that is recursive, and it checks each level of the tree. Not necessarily level of the tree, each node of the tree at the same time. So, for example, it would start with simple as if it's recursive in this sense, it checks the root, and it checks to see if it has a left child and a right child. Of course, right then and there, if there is no left and right child, it can be returned as false. Also, I would assume this method probably returns a Boolean, because the name of the method would be something.
A bool type variable.
Yes, and the method name can be, check symmetrical.
Of course.
And I will recursively check if each node has the same number of children, and if they do, check possibly that. Okay, well, eventually I will be checking the children after that, but I'm going to think of a way where I make sure on both. Okay, so I see I might possibly use a different a helper method, but I'm thinking about how I would do it now. So for now, what I will start doing is writing out the method, because I know I'm going to be starting with that at the very least. So I'm going to return a bool, and check symmetry will be the method. and it's going to be a pointer node to the root of the tree to start off anyways.
Tell me, Miss Manley, what do you see on my share screen right now?
On your share screen, I see the Google Docs.
I see.
Okay. So, yeah, so it's my work. So it's returning a bool. So I don't necessarily have to make a Boolean variable. I'll just end up returning true or false. So I'm just going to attempt to start doing this method out loud with you and expect changes along the way.
That's all right.
So for any instance, okay. So I'm looking at these examples. Thank you for the examples. So in this instance, this root, this node right here does not have a left child, has a right child, however, would be considered symmetrical. Therefore, I can't immediately actually just compare to see if they have a left or right child or not. So I'm definitely going to break up into a left subtree and a right subtree. For the very first node. Because after that, after you've broken it up into the left and right subtree, anything goes, you could say, because technically this can be this subtree can be whatever it wants. However, this one just needs to match that. So all right, I see. Okay, I see a method how I can do this.
Okay, then
I will end up dividing, dividing this binary tree into two. I know of a method where you take a tree and you flip everything over to the other side.
Mm-hmm.
So I can take, for example, the right subtree entirely, flip it as its own thing, and then do a side-by-side comparison with the left to see if there's anything off. So first step I would do, so I might end up having a method, I may, I do not know what it returns quite yet, it might just be void, flip right subtree. And that takes a pointer to the root of the right subtree. It could have been the left. I've just decided to choose the right. So I can have a base case right off the bat. This might not actually end up being recursive now that I'm thinking about it. Yes?
The method you should use to get to the bottom of the tree should be recursive, yes.
It should be recursive, okay. I may end, okay, I see. All right, I'm gonna continue with this method and we're gonna see if eventually I end up calling this method recursively, but I'm just thinking things out at the moment. So I'll create a base case first to see if the roots, yeah, this is just a base case start off. Root left equals null pointer and root right equals null pointer. This is subject to change if I find I check this later. Return true, technically.
Yes, that is a valid base case.
Now, I could have two more base case. I could, so if this has been passed, meaning one of these, okay, so I'm just creating doesn't equal null pointer or root right doesn't equal, I'm sorry, doesn't equal null pointer. This is once again just a base case right off the bat to see if it even has a left and a right subtree. If it doesn't, it is false. Because if we have passed this case, it means at least one of them doesn't equal null pointer. Oh, I'm sorry. It should be, so this is the case where it has, both of them are empty. I'm sorry, it should be this instead. Because this means one of them is, one of them isn't null pointer, but if the other one is null pointer, then it breaks. So now that that's been established, I'm finding out once I flip right subtree, how the, well, yeah, recursively, I will be checking. Okay, yes, now I understand where recursion comes into play. I might end up creating another method.
I will
This is
say
the initial one.
there is a method that would be more efficient for this kind of utility that would only require two parameters, which is the two nodes that you're comparing.
There is a method.
The method that takes in two nodes as its parameter.
Okay, so it takes in two nodes.
To check the
Oh,
symmetry.
I understand. Yeah, because you end up taking two nodes in, and then if there's ever an if one has a left and the other one doesn't have a right, or vice versa with the others, then you know it's false. Okay, so maybe instead of flipping right subtree, I can just do. I already have check symmetry, but I'm just going to call this check with node left and node right. I'm starting with this, and we're going to see what happens.
Okay.
So this, if it is reached this point in the code, it means it has both a left and a right. So I'm going to send node left. Sorry, root left and root right. Technically, I can check to see, I can make this into one method, because I can just check to see if left is null pointer, right is null pointer. Because if left and right have been sent, it is under the impression that they exist. But if they don't exist, okay, so if root left equals null pointer, or root right equals null pointer, this is going to end up being
good base case.
Return false. So technically, I'm going to scrap this. Well, no, I'm not. We're going to see.
I do believe you could do this with only one method.
Okay, I will see if I can end up reaching that point. Because we're going to see what. Okay, so and this. Okay, we've passed the case where okay, a left and a right, they do exist. Oh, I'm sorry, just left and just right. So at this point, the left and the right exist.
So you would basically be saying if left and right are null pointers, which means if both do not exist, this would return false. They are not symmetric.
Yes. Then you know what? I'm going to take what I just deleted, actually. Because this technically also works, but I need to get rid of the root. I just need to make it left and right. Thank you, by the way.
Please don't mind the sound. My helicopter has come here.
Don't worry about it. I will not let it bother my code making
If it does bother you,
procedures.
I can always mute my sound.
You are perfectly fine. Okay, so yes, in this situation, I've checked to see if they don't exist, which means return true. Else, one of them doesn't exist, which is a problem.
So there are three
Well, that's not
cases they need to check for then. You need
Yes.
to check if both are null pointers, or if both exist, you could say.
Yes. So if this has not returned true, it means at least one of them is not null pointer. So this is checking to see. So let's just say if the left one did exist, but the right one didn't, it wouldn't return true. And it would see left equals null pointer. Okay, that's false. Or right is null pointer. But the problem is if I end up using this method recursively later on, oh no, this is already establishing the left and the right. Okay. So yeah, the only reason this was called was because so interesting.
Try going from the top of the root and seeing what the variables left and right would represent in one of those example trees.
Okay, so in this case, I have checked. I know this is redundant, however, so I can I'm not going to get rid of it just yet. What's happening is the root here is 1. And then I check if it sends left and right in, which are 2 and 3. Now, technically, yeah, this is redundant, so I'm going to get rid of the first one. I'm going to technically copy it out. Comment it out. So those don't exist right now. So the first thing it does is it sends left and right, 2 and 3. First, it checks if left equals null pointer and right equals null pointer. Neither of those are true. And then if left equals null pointer or right equals null pointer, that would be in the case where if the 3 didn't exist, it would return false. Or if the 2 didn't exist, it would return false. So in this case, it is. Now from here, because the problem is the beginning of check is, okay. I see what I can do here. So what happens now is left, I'm checking maybe.
No, you have to check.
It will end up involving me checking the children
think about
it
it.
has.
For your recursion, if you look at this tree, I will annotate. See, for example, do you see my annotation?
I don't. Let me show chat. No, never mind.
No, it's in the. It should be in my shared screen.
Okay, shared screen. Oh, okay, I see now.
So you would be traveling from 1, and then you would check for the left subtree and for the right subtree. Then how would you ensure that you check both of these? Which direction would you have to go to check if they are to check your recursive?
Well, I was thinking
if we consider this left and right.
Right. So I was thinking, so after the 2, I would say if left child exists on the left subtree, for example, then you would do the same check with the right child, the right subtree, or vice versa. If you check, or you end up checking both. If the left subtree's right kid exists, then you send the right subtree's left kid into a check to see if it exists. Now this happens. It has to happen recursively. So I'm going back to mine, my tab. I might need another method to check at this point if because I would check like if left is the name of the left. So if left doesn't equal null pointer, then I would need some sort of check to see if the right tree's right, like something that involves right, because those are what's going to end up being identical.
Exactly.
But because the thing is, I can't just start sending every single kid in to check because it's not going to work. Because they're going to need to be opposites. So left is no pointer.
So in a sense, you would say that you're checking if the left of the left child exists and the right of the right child exists to return true. Would that be correct?
Well, yes. Now, obviously, there might be more to the story that we don't know about, but that should technically be that is correct. But we don't know what happens further along. But okay, so what you're saying is if I do something like, so let's just, I'm pretending here, right doesn't equal. Well, technically, okay, so in this case, neither of them. So this is, if this doesn't equal. Oh, okay, I'm possibly seeing something here, so. Check. Maybe. I'm playing around right now. So that's saying they both exist. And then, just for fun, I'm going to do this one too. But change it to left, right, and right, left. I know this could be wrong, but I'm just. So in this case, it's saying, okay, so after that point, let's say if left, right, and right, left exist, then it goes here. Then it's checking. Okay, you know what? This might be the right path. And then now, unfortunately, return. No. So maybe I might need a Boolean variable.
Let me give you the rules of the symmetric tree again as a hint.
Mm-hmm.
I'll simply write them under this image here. The first rule is that for a tree to be symmetric, both trees are empty or both are non-empty.
Okay.
And the left subtree is the mirror image of the right subtree.
Mm-hmm.
And the right subtree is the mirror image of left subtree.
Okay. Well, I've already checked. I'm checking now, right now, that if they're empty or non-empty with this. So they're either empty.
You've only got 2 more rules to check.
Yep. So now I'm checking if the left subtree is a mirror image of right subtree. So over here, well, well, actually, the first one's checked here. So I'm checking if, okay, so if left, because this is already broken up. Yeah, no, I'm keeping them separated. If left subtree left is not null pointer. Okay, now left subtree right is not null pointer, and right subtree left is not null pointer. Technically, like if this were to be correct, let's say, like, yeah, because if so yeah, before I move on to this one, so I'm gonna pretend something's over here.
I will say though, your check method is extremely close to correct.
Okay. So if
remember that for it to return the right value, it must be that this value and this value must be the same. Both of these must return true. Those are the rules of a symmetric tree.
Yeah. So so this is assuming they're not null pointer. So you're sending something in. But then eventually, okay, so that's the part. Oh, so maybe I don't even need to do this because if it doesn't, oh, you're right, because, okay. Well, not return, I'm gonna need a Boolean. So I don't even need to check this because I'm just gonna send them in anyways, and this does my job for me. I don't need this. That already does my job. And so this returns
this.
Well, no, because the thing is, if I just return, then I'm gonna need a Boolean.
Remember that both of these values must be true.
Yeah. So I'm gonna have Boolean correct start at false.
Okay.
Doesn't really matter. Okay, so correct equals this, and then right off the bat I can just do if not correct. Also, this shouldn't be capitalized. If not correct. Actually, no. Yeah, if not correct, return false, which is technically correct. So yeah, what happens is, let's just say it is starting with this example. What I've done is left and right. If left exists, it does. And right exists, it does, and neither of them are wrong. But these are checked. Correct equals check left and check right. So then now we've sent this, which is null. Whoops. This blank over here, which is null, this blank. And then, yeah, if left and right are null, return true. Cool, that's satisfied. So then boom, correct equals true right now. Now check left and check left right and right left. At that point, it sends in 4 and 5. It's not null, it's not null, it's not null, it's not null. Now technically, these are bad names because this is actually a right. And well, no, you know what? I'm gonna keep it because it's talking about the variable in the left subtree. So I'm actually gonna I'm gonna keep those names.
If you think of them as the left and right subtree.
Yeah, that's what I'm doing. So like left subtree, whatever I'm working in the left subtree right now is 4. And then 5. In that case, both of those end up being null, and both of those end up being null. Therefore, returns 2, returns true. And then correct equals check left, check right, blah, blah, blah. And then at that point, I could just return correct because it'll know what the problem was by that point. Because that's the first check. That's the second check. If this one was false, it already cuts it off, doesn't matter. And then it just checks this one. If this one's false, it ends up just returning the right answer. So
But yes. So in truth,
You're gonna get
you have indeed found the right answer.
Oh boy, I did it.
Mhm.
Yeah, and then technically, I don't need this, because this, well, yeah, like this is just in this situation where like you get the root, but somewhere else in a main method, you just send roots left and roots right in.
Exactly. If you were only to get the
Technically,
root, you would need to have a starting recursive method.
Yeah, so yeah, it starts off somewhere that sends in check roots left, roots right.
Exactly. So, so now this is indeed a correct answer. Another way to write it
Yeah,
would
I'd love
be
to see.
would be simply if you as you did a starting symmetric a starting recursive method that returns a bool and takes in the node pointer of the root, which would simply call for your root check symmetry using root left and root right. Check symmetry then would take in those node and the base case for this would be if x equals null pointer and y equals null pointer. In short, if both of them do not exist, that means it is indeed symmetric. So you could return true. Then the three cases that we've talked about is both trees are non-empty, meaning there are three cases. First, we know that x cannot be null pointer and y cannot be null pointer for them to be symmetric. That is the first case, and we need to check the symmetry between x left and y right, as you did, and check symmetry between x right and y left. And that satisfies our three rules. And that simply returns whether it is a symmetric subtree.
Wow, glad to know I was like.
No, you were on track, really.
Yeah.
No, it is helpful to think of them. Did you use the images I gave you, perhaps, to help you find?
Yes, I was able to use them. Yeah, you were able to watch me. I kind of just using the first one at the very least, kind of visualize what I had written down. And from there, I was able to see what I was doing wrong and right. And because I realized right off the bat, I can't just check if they have kids or not, because it depends.
Exactly.
Yeah, so no, I definitely did. Thank you. They were very helpful.
Then I believe that finishes it. Thank you. And you are indeed not hired.
Yay! Well, thank you.
Bye-bye. And how do I stop the record?
That's a good